And we're back. Welcome back and happy Tuesday. Today we will continue on with a little bit more about populations, but this time with an eye towards the mechanisms and meanings behind what a statistic is and what they do. But before we begin, some administrative bits. The reading by the 28th is pages 223 to 233 in the main text, section 8.3. Project 1 is due this evening at 11:59 and 59 seconds, 1 second before midnight. Please make sure that you are careful with your time. So it is of interest in many different disciplines, the study of large groups of things. Take, for example, bees. Bees are responsible for pollination, responsible for many fruits that we enjoy, and some vegetables. As the bees visit from flower to flower, they spread pollen. In fact, here in the Dover, Delaware area, if you're familiar with Pfeiffer orchards, every spring they rent or lease so-called bee boxes, mobile hives, and these bees merrily go along working their magic, pollinating the fields, giving them peaches and apples and strawberries, blueberries, all sorts of wonderful, glorious fruit. Let's look at this picture. In the bottom frame, we have rush hour traffic in Boston area, and it's pretty insane. It might take you hour and a half just to travel 3 to 5 miles. And so in the case of bees, we're interested in what happens to this population of bees because they're so important both agriculturally as well as ecologically. And certainly for traffic, we're concerned, or people are concerned, very much so, with what happens with the movement and the choke points associated with traffic, and people enterprise to find ways to relieve this congestion to try to get traffic flow, because lots of productivity is lost, and time and money and gasoline, as well as impact on the environment. And so people are often very interested in the study of groups of things, our so-called populations of things. And we saw last time the importance of visualization. Visualization can tell you something about your groups. Let's take a look at the graph on the right-hand side. Now, this particular graph was pulled from a source, and the graph was for GDP, or gross domestic product. Now, gross domestic product represents the total value associated with the goods and services produced by some entity, like a municipality, a city, town, country, and so forth. And the higher the GDP, the more economic output a region is responsible for. So this GDP, gross domestic product, is a measurement of the vitality of a population. And so we see this chart on the right of the screen. It talks about the population, and the height here of this graph along the vertical axis represents the GDP. And so this is a very compelling chart, right? It's visually pleasing, and it really gets across the point that we're trying to make about some group, in this case, a population somewhere as it pertains to the GDP. Now, of course, this graph on the left, it just looks really cool. All right, it's a pie chart, and it has to do with a measurement over a group of people. So visualization is very important, especially when you're trying to make summaries, as it were, of large groups of entities, be they people, be they bees, traffic, and so forth. So let's explore further this notion of what is a population. So last semester in stochastic computing, you learned all about various distributions, and we said these distributions govern the occurrence of data. And we used the term last semester. We said that a distribution is indexed by a parameter. And sometimes we said this distribution is governed by a parameter. So let's discuss more what we mean by this parameter. Now, certainly, the whole point of last semester, or at least part of it, was to give you experience with tools of probability, and we were concerned about how to analyze a problem and how to choose the appropriate distribution that describes the data that you're seeing, that you're obtaining from some system. Now, the various distributions we studied, they carried certain assumptions, and we spent the semester talking about these assumptions. Let's take, for example, the Poisson distribution. We said some random variable x is distributed as, how you pronounce this squiggle, is distributed as a Poisson distribution, and then we said governed by parameter lambda. And so the different values that this lambda can take on, we said lambda was the rate, and the rate corresponded to the average occurrence of events over time within so-called modules or windows of observation. And we said the probability mass function, because this is a discrete distribution, it's countable, is lambda to the x e to the minus lambda upon x factorial. So for different values of lambda, the Poisson distribution, as lambda increases, the mode, or the largest part of the probability mass, tends to push its way to the right. And then once you set a particular Poisson, you can write some MATLAB code. It doesn't take a lot of lines of MATLAB, 6 to 8 lines of MATLAB, and produce samples that adhere to this particular Poisson distribution. Now, this parameter lambda defines variations in the way this Poisson distribution produces its samples. So it's not always clear how data's values arise for some system, like the population we were talking about for the homeless population. So we were making an educated guess and saying, okay, well, based on our scenario, this particular scenario is best described by one of the distributions that we studied or some combination of them. But in practice, the distribution governs, or some distribution governs the observable data's values that you see. So if you are sampling from the population of homeless people, well, the data that you see for whatever measurements you're taking, they're going to be governed by some distribution. Well, that's the good news. The bad news is that we have no clue what this actual underlying distribution could be. We're merely making an educated guess when we cast it in terms of one of those distributions that we've studied. And so we have floating out there all the possible values of a given random variable. And so, if you're talking about temperature, temperature could be a high number, like 95 degrees, could be a low number, like today, 30 degrees. So we introduced the idea of a population. Let's be more formal now. Population is the collection, then, of all possible units of interest, everything there could possibly be. Now, agreed, we said at the outset when we started talking about population, we used the example of the homeless population in Dover, and we said you can't possibly know what they are, but they're out there. So we're going to define now the collection of all of the possible units of interest, or all of the values that you could measure. Let's define that collection as the population. So it's everything that ever could be akin to your universe of consideration. Now, when we talked about the homeless population of Dover, we thought about subgroups that make up what is possible. So now we're kind of making our educated guess about characteristics associated with the homeless population. And we said in our example, they consist of non-overlapping categories, a so-called hierarchical population consisting of veterans, families, those who struggle with drug addiction, and the aged-out foster children. So let's suppose that there's a proportion that exists that tells you what proportion or percentage of this entire collection of units or population consists of these various categories. Now, I just made these numbers up. We have veterans, 20% of the population, homeless or veterans, 15% families, Drug addicted is 30%, foster children aged out is 35. And hopefully this adds up to 100. That's 30, 35, 65, 75, 80, 20, it's 100. Yes, it adds up to 100. Phew. Okay. So let's assume, for the sake of argument, that this was the ground truth. This is actually what happens in reality in terms of the proportion of the homeless population that belong to each of these categories. Now, of course, you don't have access to this. Nobody knows what it is. That's why we sample. But to motivate this idea of what is known by the entire group of entities and why sampling is important, that's why I give you these numbers. But in reality, we don't know what they are, but they're floating out there. Let's imagine they were 20% veterans, 15% families, 30% drug addicted, and 35% the aged out foster children. And so a parameter is some numerical characteristic of that population, that set of all possible units of interest. Now, of course, this is a numerical characterization. It tells you what percentage of this set of all possible units consists of members that have these attributes. So let's make another definition. A parameter is a numerical characteristic of a population that describes something about a population, ground truth. Now, again, we do not have access to these. So what do? Well, we know these parameters exist somewhere, but we don't know what they are. We don't know what the entire group of homeless are, who they are. So we observe units from within this group or sample from the population. And so when we produced that sample, we had representatives of the group of veterans, families, aged out foster children, and those who struggle with drug addiction. And hopefully, if we've performed the sampling, if we've done that well enough, the sample is a good representation or good representative of the entire population, that group of everything that is possible. So we observe our sample from the population, and we think we've done it right, and it's a good representation. Let's assume that. So now we make statements about the entire population, the set of all the possible entities or units that are out there, by computing functions on that sample. We don't compute that function on the entire population because we don't know who they are. We only know the samples that we obtain from the population. So we make statements about the population. How do we do that? By computing functions. Now, in the case of a survey, we ask them questions. It could be a sensor that's measuring some quantity. And so a statistic, is a formal definition, is any function that you might compute on the sample. That's all a statistic is. It's the result of computing some function's value over this population, this sample rather, that we've drawn from the population. Okay, so what do we mean by function? Literally any process you can compute or calculate over the sample. So let's take, for example, you sample 1,000 individuals from the homeless population. We're going to label that set of people you sample as big X, and each of the individual samples is going to be a little x. So we have little x1 for the first sample, little x2 for the second sample, up to and including little x1000 for that 1,000th sample, that member of the homeless population. So let's compute the following functions. We're going to compute the number of veterans from our sample of 1,000 people. Let's assume that there were 200 people. And then the number of families, that's another function, 300. Drug addicted, 100. Foster kids, aged out foster kids, 400. So in this case, the function we compute over the sample, this is our sample of 1,000 individuals from the homeless population. Our function is going to return back the number of individuals from that sample belonging to each one of our categories. And that is absolutely a function. And so it can be any function that you can imagine. Now, the idea then is we can use our statistics, these functions we compute over the samples, to estimate or stand in place, an educated guess, if you will, to stand in place of the parameters that govern the entire population. So let's add some mathematical definition to this. We're going to use Greek letter theta to represent the quote-unquote population parameter. It's that governing parameter for the population. It's out there, but we don't know what it is. And now when we draw theta with this little hat over it, that caret, theta hat is going to be an estimator for theta. And so because theta is the population parameter governing the population, theta hat is going to be estimator, as it's called, for the population parameter that you obtained from the sample. And so the estimator, theta hat, is the result of evaluating your statistic on the sample that you've drawn from the population. So suppose you had ground truth, the proportion of the homeless population, the population parameter, theta vet, the proportion of veterans, theta family for families, theta addict for those who struggle with drug addiction, and theta foster, the aged out foster children. So then, by this scheme, we sample 1,000 individuals, we compute our statistic, so these are our statistics, our stats, and then we use these stats to compute these proportions, these theta hats, from the samples. And so we'd say, okay, well, we take 200 divided by the 1,000, 300 divided by the 1,000, 100 divided by the 1,000, 400 divided by the 1,000, and we get theta vet hat is 0.2, 20%. Theta family hat, the estimator for theta family, that you can use to stand in its place or as a substitute, that's 0.3. Theta addict hat is 0.1. And lastly, theta foster hat is 0.4. And so now, even though we don't know any of these quantities, our population parameters, if we sample the quote-unquote right way, and I'll stress that right way, and I'll talk about what I mean by right way. If we sample the right way, well, all of the estimators, what we do know, the outcome of our statistic, we can use them as a replacement. So we can say, aha, well, I don't know, ground truth, what the proportion of veterans are, but I'm going to assume it's 0.2. Likewise for families, addict, and foster children. Okay, so this diagram is in the book, and it looks at the relationship between parameters of population sampling and the statistic. And so you start out with your population. That's your group of all possible entities. You perform your sampling. That's your data collection. Your population is governed by parameters, ground truth, but you don't know what these are. You don't have access to them, but you can calculate a statistic over your sample. You know this outcome, and now you use it to make a general statement about your population. So you can do all sorts of things, something called estimation, hypothesis testing, modeling, as well as inference. And the idea then is now using these substitutes for these unknown population parameters, you can now make statements that are applicable to this large unknown population. And that's if you, quote unquote, produce the sample the right way. All right. So one of the issues you can have is you can have some suboptimalities. Now, we said if you sample the right way, well, what happens if you don't sample the right way? This introduces discrepancies between the population, this large unknown set of all possible entities, and the samples that you collect. Now, these errors can be two major flavors. One is a so-called sampling error. Now, with the sampling error, because you are employing a subset of the data, the sample can be off or diverge or be different from the larger population. Now, fortunately, most sampling errors, you can alleviate those errors or improve upon them or decrease those errors by making the sample size large. So that's a good thing. But there are other types of errors or categories of errors called non-sampling errors. Now, non-sampling errors arise from the fact that there's some fundamental flaw with how the sample was designed. Now, this means that the approach to sampling or the statistical method you employed or used is not appropriate for the type of data that you have. Something is being thrown away that you can't afford to throw away, or the invalid assumptions are being made. Statistics due or errors due to non-sampling errors, you cannot recover them by changing the sampling size. Can't recover. You have to change the method that you use to to do this sampling. So, for example, if we made a mistake in describing the homeless population, and let's say that there are no veterans in the homeless population for the current location, well, you're going to be very far off. You have to change your working assumptions. That's a non-sampling error. Okay, so let's see some examples of errors you can have when you're trying to perform an inference or trying to find a statistic that is a reasonable or good replacement for the unknown population parameter. You can have the wrong population. So let's say you survey 100 Samsung Galaxy users on campus about what their favorite new feature is on the iPhone. You can have dependent observations, so the observations don't stand on their own. For example, you ask students in computer science if the bookstore has good prices. Maybe things are not equally likely, right? Some are preferred more than others. There's a bias in place. You sample randomly different flights, for example, and on each flight that you randomly select, you pick 10 passengers and ask them about their flight experience. And then let's say this last one, there's bias involved, a phone poll about grocery items that are frequently purchased. So let's look at the root cause or the issue underlying each of these examples of errors. With the first one, the wrong population, well, Samsung Galaxy users don't have much experience with the iPhone. And so the statements that they make are not going to be valid because they don't represent the broad population of people who have a lot more experience on the iPhone. So your conclusions are going to be very, very wildly varying and not going to be appropriate. Dependent observations. Well, students in the department, they talk to each other more frequently. And because of this discussion, they influence one another's opinions. So I might say, hey, the bookstore doesn't have good prices. You really want to go to A Books, or you really want to go to Amazon Marketplace, or you really want to go to eBay, or just go to the library and check it out for free, for example. So students in the department talk to each other. So you're not randomly selecting from the population on campus of bookstore customers. And moreover, the particular subgroup, computer science students, they talk to one another more. Maybe might influence one another to not use the bookstore as much. This is not equally likely about the airplane passengers. So if you sample 10 passengers on randomly selected flights, the frequent flyers are more likely to be selected. So that's not representative of your general flying public. It's those who frequently use the airlines. Then there's also bias, the phone poll. If you're only calling landlines, for example, you're leaving out the population of cell phone users. And it's a fact, this population of cell phone users tends to skew to those who are younger. And so these sorts of errors, these are non-sampling errors, and it really requires you to change the way your sampling experiments are constructed and to change the underlying assumption for where you place your samples. Okay, so here's the goal for sampling. Let's say you draw examples from the population. You do this randomly. Examples are collected independently and also equally likely to be selected. That means the statistical definition of random, equally preferred, equally likely. There's no bias. The sample must also be representative of the underlying population. You can't just decide, for example, let's say there is a senior center and you decide to sample people who are hanging out outside the senior center. That's not going to be representative of your underlying population. You have to find out where the homeless congregate generally and sample from each of those locations to get access to a broader, more faithfully representative set of the homeless population. So let's take a look at so-called descriptive statistics. Now, here's an example, and this is the program on the command line window called TOP. And what TOP does, it gives you an interface like this, and it's going to show you all of the users that are on the machine, the command for the process that they're running, and they'll also give you the amount of time that your process is running on the CPU. Now, there are two different types of time. There's wall clock time, such as the time when you start a stopwatch and then stop the stopwatch. And then there's CPU time, which is the amount of time total that the process spends running on the CPU. Now, let's imagine we had a set of sample measurements for the processing time, the amount of time they spent running for each of 30 many processes. And so we have n equals 30, the number of jobs on a machine that are selected randomly, and you're going to be looking at the time they spend running on the CPU. So here's S, that's the sample, and you have the first measurement, second measurement, so forth, up to including n equals 30, the 30th measurement. So let's imagine these are the measurements. We have 3 rows of 10 for a total of 30, going from 70 to 36, then the next row 59 on through 82, and then that last row we have 38 milliseconds and 19 milliseconds. And so we have each of these times, and let's assume we wanted to summarize the amount of time that this population of programs, which is a subsample of all of the programs that run in your machine. Well, assuming that these values come from some distribution over values, you can measure all sorts of summary statistics, like the mean, which is a representation of the center of mass for your distribution, the median, which is a central value, the quantiles, which are values cutting the distribution into equal size groups, the quartiles, which are the 25% cut points, so you're cutting up your distribution at 25% of the total probability mass, the variance, which we talked about last semester, which is the dispersion about the mean, the standard deviation, square root of variance, which is the distance about the mean in context in the same units as the mean, and the interquartile range, which is the spread between the quartiles. How do the values change between the quartiles? So let's take a look at the mean. Now, this quantitative sample mean, which we note as X bar, is an estimate or an estimator that or reasonable replacement that we can use to stand in for the population mean. And so the population mean, mu, is the expected value of X, where expectation is the probabilistically weighted average. So the sample mean X bar is the arithmetic average. So we have X bar here. We take n many measurements, x1 plus x2 plus x3 up to and including xn, and then we divide that by n. That's our sample mean. And so we could try this in MATLAB, and let's try this out. And what we're going to do is we're going to take a population of 100,000 numbers, and we're going to take the true mean of that, and that's going to be hidden, but I'll show it to you because I can calculate it from my simulated population. And then I'm going to subsample some number of them, k, and compute the sample mean on the subsample. Then I'm going to measure the difference between the population mean, ground truth, and the sample means that I'm sampling. Okay, so let's switch to MATLAB. I will meet you in MATLAB. So we're here in MATLAB, and what I'm going to demonstrate to you is the impact of the sample size as to how well it approximates the ground truth population parameter. So here we have a variable population size, and we're going to create a population with 100,000 people in it, and the maximum value of this population is going to be 1 million. So we're going to have 100,000 many members, and each member is going to be a number associated with each member that's between 0 and 100,000. And so I start out and I create randomly a value between 0 and 1 million, and I do that population size many times. And so I take those values of the population that I randomize, I sum them together, and divide by the size of the population, that 100,000. So that is going to be our theta. That's going to be the ground truth mean of the population. That's going to be a population parameter. So then I go through a number of sample sizes, starting at 10, going up by 10, up to 1,000. And so the sample size can be sample size 10, then 20, then 30, then 40, etc., up to 1,000. And I take out sample size many members of this population consisting of 100,000 people. I select them by their index. So here, population size, sample size many of them. And I extract these indices from the population array in line 15. And so once I get those values, I compute my theta hat, which is my estimator. That's my X bar. Sum the values, divide by the sample size. So in these lines, I'm taking a sample from my population, and I'm computing X bar, the sample mean. And then I compare my theta hat, my estimator, my statistic, to the original theta for the population. Now, of course, I'm showing you what theta is. It's the ground truth for the population. And I show you what happens to that difference between theta and theta hat as the sample size increases. So let's save this, and let's run it and see what happens. Okay, so if I do that, we see that delta, with a small sample size, delta gets pretty big. Let's see. So delta is 36,580, then minus 270. So as the sample size gets much, much bigger, delta on average gets smaller. And so what does this tell you? Let's try a sample size starting at size, let's say, 1,000, going up by 1,000, up to 10,000. So we're going to try a sample size of 1,000 up to 10,000, going in increments of 1,000. So we're going to do 10 of them. So let's clear that, and let's try it out. Let's run it, and we'll see what happens. So as we see, for a sample size of 1,000, we get about plus or minus 2,000 to 3,000. And then when we go to sample size of 10,000, we get about 1,200. So let's see if this holds true even bigger. 10,000 going up by 10,000. And we're going to carry that to, say, 100,000. Okay. So our sample size is going to start at 10,000, increase by 10,000, and go up to 100,000. So let's see what happens here. Clear the console. Let's run, and let's see what happens. So we'll see in the beginning, with a sample size of 10,000, we get about 1,200, 2,500 plus or minus as the delta between our estimator, theta hat, our sample mean, and the original theta for the population. And you notice theta, the ground truth population parameter, does not change. The delta is first around plus 1,400, 2,500. And then when we get to 10,000, you notice 100,000, it gets much smaller. It's under 100, the delta, right? And so as the sample size increases, our estimator gets better and better and better, gets closer and closer to the theta, and you can tell because this delta starts to get really, really small. Okay, so let's switch back to PowerPoint, and we will continue forward. So we're back in PowerPoint, and we just showed that in MATLAB, when we compute the sample mean, as you increase the size of the number of samples over which the sample mean is computed, this sample mean, this estimate for the population mean, gets better and better and better, gets closer to the population mean. So let's introduce a term, an estimator, theta hat, that stands in place or can be a reasonable replacement for population parameter theta, is so-called unbiased if its expected value, i.e. on average, its value is exactly that unknown parameter theta. And so what does this mean? If you take your estimator, your statistic, theta hat, the expectation of theta hat is exactly equal to theta. Now we can show this mathematically. We take our estimator, our statistic, X bar, our sample mean, we compute its expectation. So we plug in the expression for the sample mean. That's the sum of all of the samples divided by the number of the samples, the sample size. So that's expectation of x1 plus x2 plus x3 up to and including plus xn. We divide by n, linearity of expectation. says that's just 1 over n times the expectation of the sum in the numerator. The expectation of the sum is the sum of the expectation. So we get E of x1 plus x2 plus x3 and so forth is expectation of x1 plus expectation of x2 and so forth. So now the expectation of the random variable x is mu. So we have mu plus mu plus mu n many times. So that's n times mu upon n. There's a copy of n in the numerator and denominator. The n's cancel. This gives us mu. So absolutely, mathematically, this holds true. And so such an estimator is so-called unbiased if the expectation, i.e. the average value of that estimator, that statistic, is exactly that unknown parameter mu, the population mean in this example. Okay. There's another property associated with estimators, these statistics. An estimator is so-called consistent for parameter theta if the probability of sampling error converges to 0 as you increase the sample size to infinity. So as the sample size gets bigger and bigger and bigger, the difference between the statistic, the estimator, theta hat, and the unknown ground truth parameter, theta, is 0. Said mathematically, the probability of the difference in absolute between theta hat and theta exceeding some threshold epsilon goes to 0 as n, the sample size, approaches infinity. So what this means is, as we increase the sample size, the estimator is less likely to differ from the population parameter. And so you can recover this idea. You can recover the fact that recover from the fact that you don't know the unknown population parameter just by setting this estimator's sample size to be quote-unquote large enough. And we saw a little bit of that when we had the MATLAB example. And so let's look at the variance of the sample mean and show how this happens from another approach. So the variance of our sample mean, x bar, and we said x bar is an estimator for mu, the population mean. So we set the variance of this x bar, that's just the variance, we expand out what x bar is, x1 plus x2 plus x3 up to and including plus xn upon n. Variance of a scalar is that scalar squared times the variance. So this 1 over n becomes 1 over n squared, and we have the variance of the numerator, x1 plus x2 up to and including plus xn. So variance is linear. Linearity of variance says the variance of the sum is the sum of the variance. So we get the variance of this numerator is just the variance of x1 plus variance of x2 plus variance of xn, all upon n squared. So here, the variance of random variable, we call that sigma squared. So we have sigma squared plus sigma squared plus sigma squared plus sigma squared n many times. So this numerator becomes n times sigma squared over n squared. We have a copy of n in the numerator and n in the denominator. That's sigma squared upon n. So recall, we had Chebyshev's inequality, and this is on page 54 in the main text. And Chebyshev's inequality said that the bound on the probability of the difference between a variable x and mu being greater than threshold epsilon is no more than sigma squared over epsilon squared. And so what it says that the random variable is governed by any distribution with expectation mu and variance sigma squared and have some epsilon, some threshold greater than 0, it says that this variance, you can use that variance as another way of saying that something is consistent. All right, so let's look at that a little bit more detail in terms of their Chebyshev's inequality. So we have, as our variable, we will substitute then the sample mean, x bar, and we'll plug it into Chebyshev's inequality. And so instead of using variable x, we'll substitute in x bar. And we'll use Chebyshev's inequality to demonstrate consistency. So here we go. So we have x bar here. We have mu. This is the expectation of x bar. We exceed our threshold epsilon, bounded from above by the variance of that estimator x bar over epsilon squared. So we just got done showing the variance of x bar, our estimator, our statistic. That's sigma squared upon n. And then in the denominator, we have epsilon squared. So now, if we take the limit as n goes to infinity, why do we take the limit as n goes to infinity? Well, when we talk about consistency, we said what happens between the estimator and its expectation and the ground truth parameter as n goes to infinity. And we use Chebyshev's inequality to demonstrate this. And so if the difference between the two, the probability that the two are different goes to 0, that's the same as saying the variance goes to 0. The variance goes to 0 on the right-hand side of Chebyshev's inequality. So let's take a look at this. If we have n goes to infinity, we say the limit of this bound based on Chebyshev's inequality as n goes to infinity. Well, what do we have? Well, this is a constant, epsilon squared, so nothing happens there. Sigma squared, that's a constant. Variance is a scalar constant. And we have sigma squared over n. So that n, as it goes to infinity, this numerator, right, that whole thing becomes 0. So sigma squared over n over epsilon squared is the same as saying sigma squared over n epsilon squared. As n goes to infinity, the denominator gets huge, and this expression goes to 0. And so the probability that x exceeds mu, x bar exceeds mu by more than epsilon, that probability is 0 as n goes to infinity. And so in this, we've used Chebyshev's inequality to show that our statistic x bar is consistent, right? We're using Chebyshev's inequality to put a bound from above on the probability of this expression. Okay. And so, yes, absolutely, x bar, the sample mean, is consistent. And so let's try this out in MATLAB. If the sample mean is consistent, what that means is the variance of the sample mean goes to 0 as you increase the sample size. So we're going to try this out in MATLAB. So I will see you in MATLAB. So we're here in MATLAB, and we're going to use this example to show that the sample mean is consistent. And how we're going to do this is using or pretending that we have a population of ages. So suppose we have a population consisting of 10,000 individuals. And this population of ages is going to be randomly selected to start it out anywhere between 4 years old and 96 years old. So here we're going to randomize the selection of an integer in the closed interval between 4 and 96. So we have 10,000 people who are aged 4 through 96, and that's our population. So now, in line 13, we calculate our population mean. Now, of course, because I'm constructing this population artificially, you won't in practice get to see this, but because I'm using it as the example population, you get to see it in the simulation. So now I'm going to set a sample size. Now, what if I make this sample size 10? So I'm going to select 10 people randomly within my population of size 10,000. And I'm going to select that population 1,000 many times. And then from that population of size 10, I'm going to compute the sample mean, x bar, and then I'm going to save it away, and then I'm going to compute the expectation of the sample mean. Now, my expectation of the sample mean is going to be this variable on line 35, expectation of sample mean. I take the sum of all the sample means, and I divide by the number of trials. So 1,000 times, I'm going to sample 10 individuals from this large population. The population is not going to change. And then I'm going to compute the average or expectation of the sample means. And then I'm going to plot them. And so here's my figure. I'm going to plot them and take a histogram to show you the result. So why don't we run this? And if we look at it, well, the first figure is the trial. And my trial is 1,000 trials. So we have 1 through 1,000. And each one of these points here for the blue line, that's one of my sample means. So you notice here, my sample mean for the population is this red line. That doesn't change, but my sample mean X bar, it swings wildly above and below. And that's for sample size 10. Now, in this figure, figure 2, this is the distribution of sample means. And you notice here, it has a Gaussian distribution. That's because of central limit theorem, which we learned last semester. And we notice the dispersion here above and below this value 50. So let's take a look at what happens when we change the sample size. I'm going to change it from 10 to 1,000. So now 1,000 many times, I'm going to take a sample of 1,000 individuals, and I'm going to compute the average of all these sample means. So let's try this out. And you'll notice here, my variability in the sample mean over my 1,000 trials is much smaller. It's not quite as jagged. And you'll notice here the distribution of my sample means. Well, here's 50. That hasn't changed. But you notice the variance of standard deviation for that distribution of sample means, that sampling distribution is much, much narrower. And so this is exactly what consistency means. It says that the probability that your estimator will diverge or be different from your population parameter for sample mean, and mu, where mu is the population parameter, x bar is the sample mean, is the estimator for mu. The probability that they will be different goes to 0 as you increase the sample size. So that's what consistency means. And those two properties we will use as a kind of litmus test to determine if an estimator is a good estimator, i.e. a good replacement for the unknown population parameter. All right, so let's go back to PowerPoint. I will meet you back in PowerPoint. So we just demonstrated in MATLAB in action what consistency means. So this ends what I had to say for descriptive statistics. We talked about what a population is. We talked about the sample mean. We looked at what bias means. We looked at what unbiased and consistency means, and we visualized it and got some experience doing it, seeing it in action in MATLAB. So with that, we'll end there. Again, Project 1 is due this evening. I look forward to solutions, and as usual, please stay healthy, stay safe. COVID is no joke, and I will see you all on Thursday.